begin. Welcome to this PhD defense. My name is Michael Barfod and I'm Associate Professor at DTU Transport. Sorry, I'm not at DTU Management Engineering. Before that, I was at DTU Transport. That was embarrassing. I'll be the moderator of this event. And first of all, I would like to welcome the assessment committee that consists of Professor John Preston from the University of Southampton and researcher Alfredo Núñez Vicencio from Delft University of Technology and the chairman of the committee, Professor Hailaos Saraftis from DTU Management Engineering. Yes, and also I would like to welcome Rui Li, our PhD candidate, and his supervisors, who are all over there. First, Kim Salm from Novo Nordisk, Alex Landex from Rambøll, Sten Nørbeck Madsen, also from Rambøll, and finally, Professor Allan Larsen from DTU Management Engineering. Good, I think that was everybody. And of course, also welcome to the rest of you. The schedule for today is that we will start with a 45-minute talk by Rui, in which he will summarize his PhD, which is entitled Phase-Based Planning for Railway Infrastructure Projects. The work started out at the Department of Transport, but has been finalized at the Department of Management Engineering here at DTU under the supervision of Allan Larsen. The talk by Rui will, as I said, take approximately 45 minutes, and if you exceed this limit, I will interfere and allow you to only make a brief conclusion.
Yes.
Okay?
Yes, please.
After this presentation, we will have a short break, where those of you, if you do not wish to stay for the questioning session, you can leave the room, and also if somebody needs to go to the toilet, we can take that there. And after this short break, the assessment committee will then start asking questions to Rui. When the assessment committee is done asking questions, the supervisors will also be given time for asking questions. And when the supervisors are finished, there's also an opportunity for you in the audience to ask questions to Rui. But if you wish to do so, then please notify me during the break. The whole defense can at maximum last 3 hours, so it means that we are finished at latest by 4 o'clock this afternoon. After this, there will be a reception in building 424 in room 123 at the first floor. There, that's a kitchen at the first floor. And at this reception, the committee will also announce their decision. Okay, Rui, we are ready to begin, so I'll now give the floor to you.
Yes. Good afternoon, everyone. Thank you for coming to my PhD defense activities and listening to what I have done in my PhD study in the past 4 years. I hope that you do enjoy my presentation. My name is Rui Li. I'm actually 39 years old. I'm a bit older than the normal PhD because I have been working 10 years. Then I start my master at previous DTU Transport in the study line of railway technology. Then why I continue as a PhD working on railway planning things, that was actually exactly the question I met when I work in Denmark. That's a railway infrastructure manager. I did my master at the same time I did student job at Denmark. There was a very old engineering from Sweden. After retiring, rehired by Denmark. We have a nice talk. He asked a young guy, why you decide to work for the railway and all of this. Because, you know, the train, the tracks, and they can run, woo. It was so attractive to me from the childhood. And then I talked to this old engineer. You have been working for railway in your entire life. Could you give me some suggestions and so on? And he looked at my face, gave me some surprise, say, young guy, forget about tracks, forget about the trains. If you decide to work for railways, then you work for planning, a lot of planning in the future. Then I decided think a lot about this. If I probably work in my whole life about railway planning, why not just continue as PhD and to try to improve the planning from the deep? Let's come to this research. The title of the research is Phase-Based Planning for Railway Infrastructure Projects. The fundings was provided by Danish Railway Sector Association, branch in Danish. The whole PhD took 4 years. First, I will not repeat because Miko has given the introduction. And the primary supervisor is Alan Larsen. And I have 3 co-supervisors, the former Associate Professor Kim Bang-Selling, a former Associate Professor Alex Landex, and the Railway Sector Head Steen Nordbæk Madsen from Hamburg, Denmark. That's a consultants company for railways in Denmark. The agenda for my presentation, first I will try to give some introduction about the motivation objective, and I try to give an overview about all the included papers. Then come to the detailed research questions, what problem has led to this research. And I try to introduce all the data included in this study. This will be followed by the proposed phase-based decision support system. That's the approach we developed during this study journey. How can we improve the current theory? How can we use it to improve properly the practices? I will brief the whole method there. And then I conclude the main contributions of this PhD study and the main findings. At the last was a conclusion, and I gave some suggestions for the future research. So that's the agenda. Motivation. Why I have said that I would like to focus on the planning, but actually the railway infrastructure projects is very important about 2 main factors. The first, all the projects for working on the infrastructure will be very, very expensive. It's normally involve a large cost investment. It both includes the direct cost and the indirect cost. For example, right now, Denmark running a signaling program to upgrade the whole country's railway signaling program. It's cost about 3.2 billion euro for this project. So it could cost quite a lot. For the maintenance of the tracks, it's yearly cost about 50 million euro per year. So we are talking about big money. We need to take care of how to spend those money. And the indirect cost, that's when you do some projects, you have to stop trains, and then will impact a lot of passengers. On the other side, when you do a lot of planning for railways, is the cost and time. That's track positions. We have limited time to do our projects. We have limited railway infrastructure. We either use them to do the service, to service the passengers or freights, or we do some maintenance. We have to make sure that we don't take too much time, and actually we don't have those tracks. That's why track positions is very important impact. We have limited resources, including the laborers, machine, and we need to very carefully plan the track position. Make sure that the plan is realistic, so they can finish all the work within the track position. Otherwise, they need more time than we need. Probably will cause additional delay, and cancellation will impact a lot. So time and money, that's the 2 important things we always talk about in the railway fields. Let's make sure we require an efficient planning method to take care of the cost and time, and try to make some plan which is we could save cost and time, finish within the limitation. The objective of this project is support railway project planning from we're trying to, from very practical levels, it means that some plan generated from the study could be used to guide people to find a better plan, and then reduce the overall cost without affecting railway infrastructure quality. It means that budget is always something we're struggling with if people working in the railway areas. That's why we're trying to find, to help people reduce the cost, and then we can spend the same time of cost by doing more maintenance work. This is a very general idea. If we have some scheduling problem, for example, the railway maintenance scheduling problems, then we have a lot of input, like what's the traffic for this infrastructure and what type of the infrastructure built for this part of the corridors, and all the maintenance costs related, and maintenance rules, how to make sure that the railway is maintained in the good condition of safety. All this input put our some models. The models decision support system could generate some solutions, and the solution could give some ideas or guidelines or help the experts to plan the final decision. So that's the very rough objective from beginning. And the PhD study includes 5 papers. 3 of them are journal papers. 2 of them have been published by international peer-reviewed ISI-indexed journals. That's the paper 1 and the 3rd paper. The second one was submitted to a journal. The thesis also includes 2 conference papers that look at the planning from the other perspective. Another type of phase-based planning calculates life cycle cost to compare different solutions, trying to identify the most cost-efficient solutions. Because the main contribution is focused on the journal papers, so I will focus on the main contribution from the 1st and the 3rd paper in this presentation. Here is research questions. I'm not going to look at the whole railway system because it's too complex. So that's why this PhD need to be focused and try to plan the maintenance schedule in systematic process. So the focus was decided will put on the railway balance track systems because all the data we could collect it. It's possible to find data in Denmark for the track systems. And 2 scheduling problems we will look at firstly is the railway preventive condition-based tamping scheduling problems. The problem we deal published in 2 papers, the first paper and second paper. The first paper proposing a mixed integer linear program models. I try to improve the current models from literature. The second one propose a phase-based decision support systems and try to link the gap between academic work to the practice, because you put everything into a model, give a plan. Normally in practice, Denmark experts cannot really trust and understand the model. So we need some approach to guide them why the computer models can generate such a scheduling and try to guide them understand why computer approach like this. So they could bring to minimize the gap between each other, and we're trying to convince the Denmark to use the model. And then second research question is a railway track position scheduling problem in large-scale projects. These problems, because in the first scheduling problem, we try to reduce the cost. And the second one, we look at the time. How can we better use the time to schedule all the tasks? paper 3 cover OR model to optimize the track positions. And the conference paper, paper 4 and paper 5, focus on life cycle cost and give precise-based models, try to calculate life cycle cost through a process. And so you will be able to calculate the life cycle cost for different components, and then you can compare them to see which could be better than the other. Because we try to get focus, only paper 3 will cover more than balanced track systems. For example, the catenary systems and signal systems will be mentioned in paper 3. Research data. I mentioned research data because all these the first 3 papers are based on the real data collected from Denmark. We focus on 2 corridors. The first one is the corridor between Fredericia and Odense. Here is the map for Denmark. And the main lines connecting biggest city in Denmark, Copenhagen, Odense, Aarhus, and Aalborg. And these particular corridors has been widely used by passenger trains, the national passenger trains, also international passenger trains, because the train will run from the Germany through the corridor and to the Sweden and Scandinavia areas. Also, this corridor shared by freight trains. All this maintenance record has been well documented. That's why we are possible to collect data to discuss about the tamping scheduling problems. The next level of data we collected from here, this part of Denmark, because right now all the trains running through this all the way around to Copenhagen from Germany, because here there was no fixed link. The train should run on the ferry and then transport to the rail and then go to Copenhagen in this part. In the future, we already decided to build a tunnel link because the distance between Germany to Copenhagen is quite close by doing this. So this is a project trying to upgrade the Denmark side, the railway, be ready to accept the passenger train and freight in the future from Germany. So the single track here right now will be doubled, and they are running diesel trains now, but this will be electrified in the future. So this part of data collected for paper 3, talking about how to manage the track positions. Next, I've talked about the proposed phase-based decision support system, the method we are using to plan or guide or trying to generate some better plan, so the Denmark could get some inspirations. The phase-based decision support systems is a box, as I mentioned, is a box. So we have input data, then we have some output decisions. Within the box, we have so many things need to consider. So it's better to plan them in a systematic approach. That's why we divide them into 5 phases. First phases, we try to get some data input and put them into the right format. It's not mathematical models. That's why it's not the focus for the thesis. But then we try to get some part of the data related to technical related data, because those data, how fast the track will degrade it is, how many trains run on the tracks, etc., decided when or where we need maintenance activities. So we look at the technical part of the view to say, okay, to identify the location and the time we need to do all the railway maintenance. And then because doing the maintenance will cost a lot of money, we also involve, additionally, in the next phase, involve also the cost to say, well, how do we cover or maintain all the needs from a technical point of view, but achieve a better plan with a lower cost. And thirdly, the best plan from a cost point of view is not always realistic, because if you group too much into one period, it's not possible to get budget or time to do this. That's why we have additional constraints to say, well, if we have additional constraint like budget and time, how can we manage to get a new scheduling? All these optimization phases will generate some solutions. At the fourth phase, we could compare the solutions and see which plan is better or suitable for the real case. I will use a railway preventive condition-based tamping scheduling problem, try to show you how these phase-based planning tools works. The problem defined for railway preventive condition-based tamping scheduling problem is try to find when and where to maintain, or we call tamp, the track sections over planning horizons. If you look at the data we collect from Denmark, in this corridor from Fredericia to Odense, we focus on the right track. And the track is length of 57.2 kilometers. There are 220 track sections included. Each track section contains 200 meters long. We're trying to look at 3 years planning horizons, trying to find out how to plan, well-plan the tamping. And of course, we evolve the condition-based maintenance principle. What is condition-based maintenance principle? That's basically like this. From the horizontal line, there's a time, the period going up, and the vertical line stands for the quality of the track. That's standard deviation for longitudinal level. It means that if you running trains as normal, the track quality will degrade it. It's not as good as before, so it's linear degraded. Now we have some threshold value. We also call it condition. So this is the condition. If the threshold value, if the track quality reaches a threshold value, reach the condition, it means that it could generate some uncomfortable vibration, and it could generate some safety-related accident and so on. So in that case, we need, when the status reach the condition, we need to do some tamping or maintenance to improve the status of the tracks, and then degrade it and then do some tamping like this. So this is a condition-based tamping principle. We decide the tamping or maintenance based on the condition. Let's talk about the technical optimization. We'll only look at how fast the track will degrade it and generate such schedule. And here you can see there are 220 track sections will be planned for tamping. And here is the time from 0 to 10 in this case. Each number represents 3 months. So it means one is 3 months later. And here, when we look at all the track geometries, track degradation rate, and transition curves, etc., we generate, because you can see 2 track sections need to be tamped at the first period, and then some other section will be tamped accounting to this picture. We're using optimization models at the background to minimize the number of tamping, to see when is the possible latest time to do tamp for each section. Yes, and this is exactly has been done in literature by others, saying they assume that if you minimize number of tamping, then we minimize the cost. But is that true? Minimize number of tamping equal to minimize tamping cost. That's not true, because from this picture you can see you have to go back to tracks almost every single period to do some tampings. You need people to do that. How can we improve this? So far, we didn't involve any cost. We only involve technical data at first phase. So how can do this better? That's the next steps. We try to involve some cost by consider all the technical data, but also the cost, how to maintain these tamping needs in a better plan. Actually, we get this. We change the objective function from minimize the number of tamping to minimize the relative cost. You can see that we generate the scale like this. We are not going to the track and do all the maintenance every single period, but we try to group them and do them together so we can achieve scale or economy. So the cost could be reduced. But you can see that from here, that's the tamping needs. Technically, we need to tamping, but we generate here. Some tamping has been moved earlier. In that case, means that if you do some tamping earlier, probably in this same section, you need more tamping at the end. But otherwise, then you have some reduced fixed cost to go to the track at each period. When you balance those costs, the optimization program will give these optimal solutions. And here is, from cost perspective, is better than this plan. And I also used to show the plan to Ben Denmark did not be like this, because it's true to group them. And when we compare the cost, the plan, the tamping cost, doing tamping exactly here, it doesn't really change a lot. But the running cost, the fixed cost, we don't go to the track every time, will save a lot. In balance, we get a lower cost schedule. But in this phase, we are covering the tamping needs with less cost. And the last, as I mentioned, if you group too much, then you have to do a lot of work as a single time period. That will probably will exceed the budget. And how we respect the budget and the time. Then we solve this problem by constraint optimization. We put some budget, saying this is budget you can't accept. And the previous tamping schedule, generally this red, they do tamping at the first period, the fifth period, and eighth period, and the second tamping batch, they're doing too much, exceeding the budget, and then we have to rearrange them to 4th time instead of 3, and we get this realistic tamping plan. All this can be done by the constraint optimizations. And this is not the only one to do optimization. You can also consider other conditions. For example, the planner preference when they would like to do maintenance and so on. So it could generate multiple schedules. So after this phase-based planning, you'll be able to have a lot of different schedules from different focus and perspectives. In that case, can support a decision maker. Here is the general idea about decision support system. We generate different solutions, and the experts could adjust which one could be better than the others to fit the reality. Now we talk about the cost already. So planning railway maintenance or infrastructure project involve a cost and also time. The third paper, we try to focus on the time, how to manage time better. Track positions, we have basically 4 types of track position in Denmark doing the projects. We have, if we divide a day, like a Monday, the daytime and the nighttime using time slot, and weekends by just 1 time slot. You can see we have interval positions that the work was being implemented during the weekdays. And the train, running train will be reduced for example, used to run 4 trains per 4 trains per hour could reduce to 1 train per 2 hours. And then you have possibility to work between the train running intervals. Then we have night positions. We work in the night. And we have weekend positions. Then we start from Friday night and cover the weekends. And for some summer holidays, it's also possible to close the track totally. So the passengers drive their personal car or use bus instead. These are the 4 type of track position we are trying to optimize. So it's a railway track position scheduling problem. And in this scheduling problem, we are trying to find out when to implement which task under which track positions. If you look at the data we collected from Hinsted Holby project, you can see those 10 railway works need to be considered, and each of them have a big volumes. And you have working sequence. Some work need to do before the others. And we have other operational constraints, like at the one time, maximum 3 tasks can do together, etc. So it's a huge amount of work. If consider using Excel or other tools, is almost impossible to find out in a short time. So we built the mathematical models and try to look at the different given scenarios. The government and Denmark or DSB discussed that we could have some different scenarios. The first scenario is that we have 6 months total closure during 2020. And then you're free to do a night position or interval position and other positions in other time. The second scenario is that we close the track for 10 months in 3 years in summer period, and then we close 13 months in 4 years. We have a total closure in 2020 because a big bridge needs to be renewed, and during this time period, the track will be closed anyway. So the government need to know which which type of scenario would be better and how much difference if we plan them, how much cost difference from them. We also have 2 options. We could ask some supplier from Denmark, work for the projects, how much it's going to cost, and we can also hire some supplier from Eastern Europe with a lower labor cost to see, yes, and how much it's going to cost if you ask them to do the job in 3 scenarios. Again, it's a larger scale project. It's almost impossible to sit down and manually do the calculations. So after building the models, here is the output. We have scenario 1, 2, and 3. That's the scenario will close the track, increase the total closure time. Here is 13 months close time in 4 years. In general, it has the lowest cost compared to the other scenarios. And then this bar stands for the standard supplier in Denmark. So if we are trying to find somebody with 35% lower labor cost, it could achieve about 3.2% of total cost. All the scenarios could cost around 1 to 1.2 billion Danish kroner to finish 10 tasks. Yes, if we close 3 months less, then we have about 2% cost increased. And then if we very tough to do 6 months, and then the cost will increase about 5%. Then we have another 3 scenarios, because close weekend every week is typically not possible in Denmark. So S1 comma, S2 comma means that we only possible to do weekend position once per month. So you have, after calculations, we can see that we have increased the total cost tremendously by doing this. again, the saving from the supply with a lower cost is very limited. It's not that much. Here is some practical working schedule from the models. So the model is give some cost pictures, but also suggest when to do which task at where. We have 4 positions: total closure. I think this is weekends closure, night closure, interval closure. And here is the list of the work tasks from 1 to 10. If you look at the all closure the first year for the scenario as to comma, then we in the total closure we are trying to do this work 1 together with work 2, and then part of this work because at the same time there are only 3 parallel work are allowed. So the plan gave some suggestions. So the course you can see from previous pictures actually have some feasible plan. So we hope that this plan can give some inspiration for the planners. Yes, and we have covered the cost and the time by these papers. The main contribution and the findings from my research. The main contributions, we tried providing or developing a method of phase-based decision support systems that is able to solve the railway tamping schedule problem in systematic processes. And we improve the knowledge of the new mathematical formulations on the railway preventive condition-based scheduling problems and obtain the cost reduction compared to the existing literature, because the technical optimization was the same as almost the same as the current literature. Defining a new track position scheduling problem. This problem is totally new from literature, and provide decision support in large-scale projects with multiply construction works at the primary planning level. And if you go to the tamping planning, the contribution, particular for the OR model, is that we provide extra practical cost components. So minimum number of tamping, that's the minimum of the cost, has huge differences. And we also provide some temp values for cost. So the tamping will be scheduled at the latest possible time for one section, instead of doing at other sections. And we contribute a more realistic estimation for tamping recovery. What's the meaning of that? I'll explain a little bit later. Compared to the literature, which is the number of tamping to a minimum cost, the minimum number of tamping will cost 59% more expensive. So a huge amount of money could be achieved, but of course it's not feasible all the time. We have to consider the constraint optimization. About this realistic estimation of tamping recovery. From literature, when you do tamping, you improve the data of the track quality by the literature only use one type of recovery, saying it mainly depends on the quality before tamping. So this is a calculation how much it can improve depends on the quality here. But from the running the case, we realized that it's possible if you only use this to calculate the next, because if you tamping 2 sections right after next, then it's possible reaching a track quality better than tamping before. Like a car, if you have a new car, then you maintain it many times, you never be better than a new car. So it means this is not realistic. It's not improve the track quality better than the previous tamping. So it has to at least the same as before or higher. So this is a more realistic estimation of the tamping recovery we're using in literature. In the literature, they are using a red line, and in our models, we are trying to use the blue lines. So this could achieve 10% underestimation of tamping cost. By minimizing the net present values, we can necessarily reduce unnecessary early tamping. Means that, for example, if we have only one tamping at a period for these sections, in the literature, they could do tamping any period before it because they didn't count the value of time. But if we put some interest rate, the lower tamping will cost less. So the tamping will push always to the to the later stage. In that case, at the end of the period, we have 2% improve for the quality for all sections in general. Contribution to the track position scheduling problems. We defined a new problem in the literature. This is not be defined before. A new method transfer the nominal price into track position-based price. I haven't presented in this, but it's included in the thesis. By using the real price, we can avoid in cost and estimation about 28%. And there is a new OR model. It can be used as efficient tool because in 2 hours' time, we are almost reaching the optimal solutions. So in that case, if we have a big pool of alternatives, we can use the models that try to get small pool in rather faster. Contribution for the conference papers, I haven't presented in the precision, but generally it's introduced phase to calculate the life cycle cost, not only include the direct cost, but also include some cost from passengers and train operators, etc. So we'll be able to find the overall cost from a wider scope. A phase-based process to estimate cost to calculate life cycle cost from phases, and considering multi parties, because if you only look at direct cost, that's benchmark. And you need also consider some operators because they are running buses and to replace when the track is in maintenance, etc. So at the early stage, you can involve all the relevant cost. And the findings, the strength of a phase-based approach, because we're solving the maintenance scheduling problems could divide a complex problem into solvable subproblems. And visualize solutions from different perspectives, like from a technical, we know where we should do technically tamping, and then how can do better maintenance with lower cost, and then fit the other constraints. So this can improve the understanding and link the gap between the practice and academic. Because if you only get one solution from the you can do the tamping like this, but they ask, well, I need a tamping here, why you do earlier? Then you have some discussion, but if you provide all this, I understand you need to tamping this, but if you do this, then you can achieve a better price, etc. Then can break the gap and understanding. An importance for life cycle cost. Considering a railway infrastructure project from a life cycle cost point of view, could help infrastructure manager to open eyes to the asset's entire lifetime. Some new tracks like slab track, if you compare slab track and ballast track, or you can compare the wooden sleeper and the concrete sleeper. The concrete sleeper, for example, could cost more at the beginning, but required less maintenance on the way. If you look at the cash flows, some components could be cheaper if you look at all the costs in the lifetime, because they require less maintenance and have a longer life span. But the wooden sleeper need a lot of maintenance and certainly need renew after a shorter time. Then after annuity of the life cycle cost will be lower actually by using the concrete sleepers. So in this life cycle point of view, you could find a right solution. The conclusions and suggestions for future research. Conclusions, the thesis contributes to the OR literature and the non-OR literatures. The contribution cover phase-based methodology, try to improve the understanding, and then provide the OR models and the computer results using the real data and generate a lot of savings. Estimate cost from life cycle cost perspective can be used to identify most cost-efficient planning solution in the long run. The proposed phase-based decision support system and the new OR models can give practical scheduling advices. So from beginning of this study, we are trying to build some models could be used or give some inspiration for the infrastructure manager. And hopefully we will reach that. The phase-based decision support proposed by this thesis has a great potential to support decision-making in practice. That's the conclusion. For the future research, the same phase-based concept by consider first the technical data and economic data and constraints could also be used to other system planning, like a catenary system, railway switches, and track renewals, because all these planning involve the technical status and economic factors. Heuristics as a method could be developed by adding some geometry locations, because when you plan the track positions, you need to know where the track needs to be upgraded and so on. These are not considered in our model from primary planning levels. But if you want a very detailed planning schedule, then you need to know where you need to go there. And then you need to know the track layout in the location, so you can, for example, if you have multiple tracks in the station, then you probably can implement more than 3 tasks at a time, and so on. So this could be adding into the study to find a more detailed plan. I think that's my presentation. Thank you for listening.
Thank you. Okay, we will now have a 5-minute break before we proceed with the